Welcome to another wonderful day in Calculus 3. Let's do the rest of vector fields. Here we go. So definition of gradient fields, potential functions, and equipotential curves. So if you've got little f here, that's the potential function, and it's differentiable in either R2 or R3, 2D or 3D. The vector field given by f equals the gradient of the potential function f is called a gradient field, and the function f is known as the potential function for that vector field. Now, the level curves of that potential function, we did some graphing of those have a special name. They're called equipotential curves, and that's the curves on which the potential function is constant. So let's do a little example here so you can kind of put all these thoughts together. We're going to find the gradient vector field f for the potential function given by fxy equals x squared minus y. So this is the opposite of what we did last time. Last time, when we found a conservative vector field, we learned that is understood to be somebody's gradient. And whose gradient? Mama, the potential function. And so then we had to go recover mama, and we had to do that by integrating and partially integrating and so on. Well, what if you're given mama and you want to find the gradient vector, the vector field that goes with the mama? So we're going in the opposite direction now. Now you're given mama, go get the gradient. And this is easy because you guys got gradients all the time in a previous module in this course. So easy peasy. And then after that, we'll plot the gradient field together with a contour map of f. Okay, in other words, we're going to graph the equipotentials. Now, we did this already, but now that we have these other definitions, we'll have this down. Okay. We're going to do some flow curves also. Okay, so f, and put a vector on top. I want that notation. That is going to be equal to del f, that's the gradient. And we know gradients are vectors that have the partial derivatives as components. Sure we do. We did this all the time. And then this is an easy function to get the gradient for. The derivative with respect to x is 2x, and the derivative with respect to y is -1. Okay, so we just did part 1 of example 3. We got the gradient vector field. Check. Done. Now what? We got to go get those equipotential curves there. Yeah. So how do we get those? The equipotential curves. This is where you take the magnitude of your vector field and you set it equal to, or excuse me, let's get the level curves for the function fxy, set it equal to a constant. So this is going to help you to get the contour map. So these are level curves. So how do you do that? Well, you're going to go x squared minus y equals a constant. And what the heck is that? I don't know. Let's rearrange this equation a little bit. I'm going to solve it for y. Not too hard. And this looks like it's going to be a bunch of parabolas, depending on what c is, the constant c. So if we just pick different values of c, we'll get some level curves. And then what we'll do, those are going to be the equipotential curves. And then we'll graph our vector field. We're going to make a chart and everything. So some students were asking me, well, how do you want us to graph these vector fields on quizzes and exams? I want you to do what we're doing here in class. You get these equipotential curves. And if it's not conservative here, you don't have a potential function, so you just set the magnitude of the vector field equal to a constant, like we did at the beginning of this section. And then you pick some points off of one of the curves and make a chart. So we're going to do a similar thing. How about if we let c equal 0? If you graph that, that's just going to be the parabola y equals x squared, like that. There it is. That's c equals 0. So for c equals 0, if I make a chart, I'm going to pick some points off the parabola, and then I'm going to graph the gradient. Okay. So I know that 0, 0 is a point on my parabola. Okay, what would be the vector associated with the point 0, 0? If I plug this point 0, 0 into the gradient, I get 0, negative 1. And if I were to graph 0, negative 1, and since it's just the origin, it's already in standard position, it'd be a vector of magnitude 1 pointing downward. Okay, that was easy. Let's pick another point that we know lives on the parabola. Well, I know that 1, 1 is a point on y equals x squared. So we know that. So if I put the point 1, 1 in my chart, then what is the vector that goes with it? So just plug this into the gradient and you're going to get 2, negative 1. If you graph 2, negative 1 in standard position by finding the point 2, negative 1, and then drawing a vector starting at the origin as the initial point to this terminal point. Now don't leave it there. You have to translate it. So what do I mean? You're going to move this vector so that it is starting at the point 1, 1, points in the same direction and has the same magnitude. It looks like it's kind of like that. Okay, so that guy. And then let's pick a couple more points off of this parabola here. I don't know. And we could pick a point over here, 1, negative 1, or excuse me, negative 1, 1. Negative 1, 1. And if we put that point into our chart, we will get the vector negative 2, negative 1. And if you graph that in standard position, you'll get like this vector here pointing sort of down and to the left, and then lift it up so that it's sticking out of the point that it's associated with. That's the negative 1, 1. There he is. And I can pick one more point off this parabola. It looks like the further away you get from the origin, the larger the vectors become. But if I pick this point over here, like 2, 4, on the parabola, negative 2x would be negative 4, negative 1. Negative 4, negative 1, ooh, that's like that. Oh, excuse me, this is going to be positive 4. Negative 2. So positive 4, 1 is going to be like pointing way over here, like that. So if I graph that over here, like that. Okay, so that's one graph there. So let's pick one more parabola to do business with. How about, I don't know, we could do c equals negative 1. So if we let c equal negative 1 in this, we'll have x squared minus 1, but that's y equals x squared plus 1. So that's just a parabola translated up by 1 unit. So these values here have to do with c equals 0. So continuing my chart where I plug in some points from our new parabola, the one that's translated up a unit. So just pick some points off of that parabola and plug them into the vector field, which is our gradient, and then just graph those. I want you to start noticing, though, something very specific is happening here. For this gradient field, all of the vectors are indeed orthogonal to the level curves, as they should be. We learned that last month. So that's one of the key properties of a conservative vector field, a gradient. So if I pick, I don't know, like let's pick this point here. That's easy, you know, the point 0, 1, then it'll be the vector 0, negative 1. So that's still going to point down. I'll pick a different color here. But what if I pick a different point on that parabola? I don't know, you know, pick something like, what if x were 1, then you would have 2. So the point 1, 2 is right there. When you plug that into your vector field, I would get 2, negative 1. So that's going to be, again, you're going to get vectors like this. So all these vectors are going to be orthogonal to level curves. So I like to graph these on my cool app here. So the way I can do this is I pick a 2 vector equal to another 2 vector, And here, the x component is 2x, and the y component is always -1, not y minus 1, -1. And if I graph this vector field, I get a better view of it here. You can kind of see the look of it. Those little dots are where the arrows are supposed to be. So that's kind of nice. It's an interesting looking vector field. It's kind of hard to tell what the level curves are and that they're parabolas, but at least you get a feel for the curve or the field and what it looks like. Okay, so there you go. So please notice that the gradient field is orthogonal. So I'm going to write it down. It's that important. Notice that the gradient field is orthogonal to the equipotential curves. I can't write today. Equipotential curves. So why are they equipotential? Because if you graph these guys, you would stay at the same altitude, if you will, for the potential function. So this is especially for people that are really involved with physics. Why are gradient fields important? Well, because of the physical meaning of the gradient. So let's go over these points here. If a potential function f represents a temperature, say in some conducting material, then the gradient field evaluated at a point, it basically points you in the direction that the temperature increases most rapidly. We studied this last module. And so according to basic physical law, heat diffuses in the direction of the vector field, the opposite of the gradient. So this is because entropy is increasing. If you take a thermodynamics class, you'll learn that. And that means that the temperature will always start cooling off, decreasing. Okay, so you're going to have it decrease most rapidly at that point. And you might even hear this phrase, heat flows down the gradient from relatively hot regions to cool regions. That's how heat operates. Like it likes to get colder. And similarly, water on a smooth surface tends to flow down the elevation gradient. Down the, well, because of gravity, you know. So let's do one more example in this section. Again, putting it all together, but this potential function is really wacky. So I kind of like this example, and I pulled this one off of your homework. So you may see something like it there. So again, they're giving you the mama function. They're giving you the potential function, and they want you to find the gradient vector field that goes with it. Fine. So the question is, how do we get this gradient? So I'll call it del phi, and you're going to, so I'm going to get my phi partial derivatives. How do you take the derivative of arctan? Does anybody remember from calculus 2? ddx of arctan of u is u prime all over 1 plus u squared. Does anybody remember this from calculus 2? U prime?
Yeah.
So here the u is y over x. So you got to be careful though on when you're doing a partial derivative. Okay, let's check it out. So our gradient field, which is the gradient of phi, we're going to first take the derivative of this arctan function with respect to x. So the denominator is going to be 1 plus the u squared, where u is y over x. But what is u prime? And keep in mind, you're trying to take the derivative of y over x with respect to x. So I just want you to do a little side note here. When you're doing y over x, that's the same as y times x to the negative 1. So if you're going to take the partial of yx to the negative 1 with respect to x, using the power rule, you'll get y times -1 times x to the -2 power, but that will be negative y over x squared. So negative y over x squared will be the numerator for that partial derivative. And then when we get phi y, taking the derivative with respect to y, the denominator will still be the same. You still got your 1 plus u squared. And then we're going to have the numerator be the u prime, the derivative of y over x with respect to y. But that's 1 over x. Now clean these guys up. This is messy. I wouldn't give you full credit. It's right, but I don't like a fraction inside of a fraction. And that's known as a complex fraction. And both of these are complex fractions at this moment. Well, how do you clean up? Well, this thing, if you think of the y over x squared as multiplying with this, it's a little bit easier because then you can multiply these two denominators. So you can distribute the x squared and then reduce. So when you do that, you get a nice denominator there.
Professor, what happened to the negative in front of that y over x squared?
What happened to it? I don't know. I accidentally had it disappear. Thank you. It should still be there. Yep. Now, you're not as lucky with this guy. Like this guy, if you're like, well, you know, I'll multiply these two fractions together and I'll distribute. But the problem is, after distributing this x, you still have a fraction because only one of the x squareds cancel there. So this is still yucky. Yucky meaning it's still not simplified enough. Well, how do I clean it up? Well, you multiply by a very special version of 1. Well, what's that going to be? You got to pick it right. And I claim if you multiply by x over x and then distribute this x, it should look a lot nicer. So now you have your gradient field without any complex fractions in it. And so it looks much prettier. Okay. And if you were to graph these by making a chart and so on, it would turn out that you would get these red arrows, you know, and the further out you get, the larger they get. And notice these arrows are indeed orthogonal to the level curves. Where the level curves of arctan are these rays directed outward. So it's kind of fun. It's kind of a cool looking graph of the gradient field with those equipotential curves. And of course, now for one of my favorite memes, hey, Mr. Fox, is there a reason why you're standing on your chair? And this is talking about kinetic energy and potential energy that we were talking about. And if you've taken physics already, this will probably be a little bit more funny. And if you haven't taken physics yet, well, you may not be as impressed. But anytime you lift something up, it increases its potential energy. So like my books in my bookcase here, the books on the higher shelf have a higher potential energy than the ones here at the bottom of the shelf. Why? Because if they fall, they have a bigger potential of hitting me in the head and hurting me. More potential energy. So here we go. And then the kid says, oh, it's to boost my energy. I was feeling a bit sluggish. And then the physics teacher, or then he keeps going. By my calculations, standing up here gives me an extra 300 joules of potential energy from gravity. And then the physics teacher says, but you had to expend energy to get up there, so your total energy hasn't increased. And then the student says, why had Steve lift me up? And the physics teacher starts thinking, fall break can't come soon enough. And then the student goes, hey, thanks for teaching us this stuff, by the way. I love that. And then this one, can easily do vector calculus, cannot balance own checkbook. I don't know, sometimes I feel like that. So that concludes vector fields. Congratulations, you now have a full introduction to vector fields.